Good morning, guys. I hope you guys are fine today. So, today we are going to speak about sex linked genes. We are going to speak about sex linked genes. Okay, so we've got two types of chromosomes. We've got, sex chromosomes, also known as gonosomes, and autosomes. Okay, so sex chromosomes and autosomes. But in this case, we are speaking about sex linked genes. So we are going to focus on gonosomes, in other words, sex chromosomes. So they not only determine gender, they also carry other genes. Alright, so sex chromosomes carry genes. Alright, so for example, I've got two types of chromosome. I've got X chromosome and Y chromosome. X chromosome and Y chromosome. So if for example, women, they are XX, because we speak about, when we speak about haploid and diploid, we say two sets of chromosomes is something that has to do with body cells or somatic cells. So XX is a woman and XY is a man. So Y is Y chromosome is what determines the male sex. Okay, the absence of a Y chromosome means that the person is a woman, and the presence of a Y chromosome means that the person is a man. So Y chromosome is very small and carries few genes. Don't worry, we've got a lot of illustrations here, pictures, right, diagrams, and you understand. This is just an introduction. So that in that case, if the recessive allele, all right, this is recessive. If the recessive allele appears on the X chromosome of the man, it will be visibly part of his phenotype. Okay, so in the case of male, right, man in this case, they just have one X chromosome. So if what we are studying appears or is on the X chromosome, if the allele we are talking about, the gene we are talking about, is on the X chromosome, right? And taking into account that males only have one X chromosome, it means that the presence of a defective gene on that X chromosome is going to mean that the person will be affected by that defective gene. So you will have the genetic disorder in this case. So if the recessive allele appears on the X chromosome of the man, it will be visible on the phenotype. Okay? So, for example, when a woman has one recessive allele, it will not be visible in the phenotype because she is XX. So one recessive allele in one of the X chromosomes is masked by the dominant allele on another X chromosome. Right? So when a woman has one recessive allele, it will not be visible in the phenotype. This is due to the fact that she has a second X chromosome which will possibly carry the dominant allele and which will dominate the recessive characteristic. So in this case, the dominant allele in one of the X chromosomes masks the recessive allele on another X chromosome. This is in the case of a woman. Okay. So there's this case of a sex-linked genetic disorder, right? The color blindness. So this defective gene appears on the X chromosome. So we call it red-green color blindness. So it's a good example of a sex-linked gene. Okay, the gene for color blindness is recessive and sex-linked. For example, when a woman inherits the recessive gene from both her parents, which is really rare, right? Very, very rare, right? She will be colorblind. So what we are saying here is that it's common to have men that are colorblind than to have women that are colorblind. It is really rare to have a woman that is colorblind. Why? Because they have two X chromosomes. So the presence of a recessive allele in one of the X chromosomes is going to be masked by the dominant allele on the other X chromosome. That's why it's really rare to see a woman that is colorblind. So for a woman to be colorblind, both recessive genes must be on both X chromosomes. Okay? So, which means that 1 out of every 12 men is colorblind, while 1 out of every 200 women is colorblind. So you can see this discrepancy here. You see the discrepancy here. So 1 out of 12 cannot be compared with 1 out of 200. It's really rare, seldom for women to be colorblind. So this is just an illustration of what we are talking about. All right? An illustration of what we are talking about. So you can notice here that the X chromosome is bigger, okay, than the Y chromosome. Like more than, in this case, twice as big as the Y chromosome. Okay? So, in this case, the recessive gene for color blindness is on the X chromosome. The Y chromosome does not carry any gene for color blindness. You can notice that. Okay, so the gene for color blindness is on the X chromosome. So in the case of a male is XY. Alright, so if the recessive allele is on the X chromosome and you are a male, definitely you will be colorblind. But if the recessive allele is just on one X chromosome and you are a woman, you won't be colorblind. You will be a carrier of the recessive gene, but you will have the dominant there to mask the recessive, so you will be normal. Normal, you know what I'm like, not actually normal, because normal means that you don't carry the recessive. You'll be a carrier, but with the normal phenotype, which means that you won't be colorblind. Okay, so male individual will be colorblind because only the recessive gene is present, but female individual will be normal, or a carrier in this case, because the dominant normal gene will dominate the recessive one. So the dominant will mask the recessive allele. Okay, so which means that a colorblind man can only transfer his recessive gene to his daughter on his X chromosome. You understand what I'm saying? So what I'm saying is a colorblind man can only transfer his recessive gene to his daughter, because he can't transfer it to his son. Why? Because he actually, in the case of a son, a man is going to contribute, with the Y chromosome. Okay, what the man passes down to the son in this case is the Y chromosome for a boy. So it means that it is impossible, for a man to transfer his recessive gene, on that is displayed on the X chromosome that he has to his son, because he only passes down his Y chromosome, because that sperm was a Y chromosome sperm, if you understand what I mean. That sperm, there's two types of sperm. Some sperms, we can call them female sperms and male sperm. Female sperms, they have one X, and male sperms have one Y chromosome. So female sperms, X chromosome, and male sperms, Y chromosome. So if you're a boy, it means that the sperm that fertilized the egg of Your mother, that one, if you were a boy, that sperm was a Y chromosome, and the egg is always X. So Y and X is X, Y. You are a boy. If that sperm was a female sperm, so it carries an X chromosome. Okay, it carries an X chromosome. So that X chromosome sperm fertilized with an ovum or egg in this case is going to be XX. So it is impossible for a colorblind man to transfer his recessive gene to his daughter. To his daughter on his X chromosome. Oh, sorry guys. It is impossible. What I mean is, it is impossible that a colorblind man can transfer his recessive gene to his son. But a colorblind man can only transfer his recessive gene to his daughter. He can't transfer it to his son. He can't pass it down to the son. Okay? He can only transfer it to his daughter. So the daughter will probably be a carrier. And if she is a carrier, she will not be a colorblind person. Why? Because she will have a dominant allele on the other X chromosome to mask the recessive allele on another X chromosome. So on one of the X chromosomes there is a dominant gene, and on the other there is a recessive gene. So she will be a carrier, and phenotypically speaking she will be normal. Alright, just a carrier of the gene but normal, which means that she won't be colorblind. Why? Due to the fact that her other X chromosome most probably carries the normal dominant gene, and if it does, she will be normal. So if I'm going to speak about that with the diagram, if this daughter has a son, right, she can transfer the recessive gene to him on one of her X chromosomes. So you understand what I mean, guys? So this man can only transfer his recessive gene to the daughter. The daughter will be a carrier, but normal phenotypically, not colorblind. But if this daughter has a son, now she can transfer the recessive gene to him on one of her X chromosomes. So what does that mean? It means that these men can transfer his X chromosome only to his grandson. He cannot transfer the X chromosome to his son, but only to his grandson through his daughter. You see that? So this will result in color blindness in this case. The grandson will be colorblind, if you understand what I mean. So let us see this example here. In order to make this explanation easier, let us study the family tree below. This is the rectangle representing the male, and this oval shape representing female, and this bolded X representing X chromosome with the recessive gene for color blindness, and the X that is not bolded is the X chromosome with gene for normal color sight. Now, suppose now that a man that is colorblind is married to a woman that is normal. She is not a carrier, she is just a normal woman. Both of the X chromosomes of this woman are normal. They don't carry the recessive gene. So the man has got an X chromosome that carries the recessive gene. And as the man has only one X chromosome, because the Y chromosome does not display this kind of gene, this man now is colorblind. So now they have the probability of having a son that is normal, because this son is going to inherit his X chromosome from his mother, okay, and the Y chromosome from his father, actually, of course. So all sons of this couple here will be normal. All sons will be normal because the X chromosome always comes from the mother, and the mother is normal. She is not a carrier. But their daughters can be they can be carriers of the recessive gene. You see that? They can be. So in this case, they've got a daughter that is a carrier. You see? Yeah. So, of course, all daughters actually here will be carriers because the father is colorblind. So, all daughters will be carriers. Now, this daughter is now married to a normal guy. This guy is not colorblind. He's a normal guy. And you can notice that now they can have a son that is colorblind. You see what I'm saying? So, that means that this man here, the first one, okay, can only pass down in terms of male, okay, when we're talking about males only, he can only pass down his X chromosome to his grandson. He cannot pass down his X chromosome to his son, only to his grandson through his daughter. This is what we are trying to explain in this family tree. So, you can notice what I'm saying is here. Okay, so they've got her daughter now has got a son that is colorblind. So, which means that you, as a man, if a colorblind man, you can only transfer that X chromosome for color blindness to your grandson through your daughter. You know, that's what I mean here. Yes, so this is how you do that. So we also have another case of sex-linked diseases, you know, because remember we are talking about sex-linked genes. So this gene is also carried by an X chromosome. So haemophilia or bleeding disease is also a sex-linked characteristic or trait that is much more serious than color blindness. Why? Just look at the symptom. Blood takes a long time to clot due to a lack of an important blood clotting factor. So even the smallest cut will bleed a lot. You know, that's why it's dangerous, because the person loses blood. You know, you can't live without blood, you know. So if they get wounded, they can't heal as you can, you know. They can't heal. It takes a long time to heal, and in the meanwhile, the person is losing blood. So this condition is a genetic condition, okay? It has to do with a gene on the X chromosome. Now let us study this. So you notice here that X superscript capital H is X chromosome that carries the normal gene. X superscript small h, small letter, no, lowercase h, lowercase, that is X chromosome that carries the recessive gene that results in haemophilia, and Y does not carry the gene, of course. Okay, so if Y does not carry the gene, we can't put the superscript H or Y there. Okay, so if you see a woman can be a carrier, so X superscript capital H, X superscript small h. And a man can only be normal when the X chromosome does not have the recessive gene. Instead, it has the dominant gene. You can notice here. And a woman can only be normal homozygous. A normal homozygous female individual is X superscript capital H, X superscript capital H. And as long as a man carries the recessive gene, that man is hemophilic. And it's really rare to have a female individual with this condition, because for them to have this condition here, they must carry the recessive gene in both X chromosomes. So double recessive, very rare. So it's seldom, right? Okay. right now. So a genetic diagram using the symbols above will look as follows. A female that is a carrier, okay, which means phenotypically normal but a carrier of the recessive gene, is crossed with a male that is normal. You can notice that in this diagram here, okay, there's how do we actually do this? The probability of having a normal daughter, the probability of having a daughter that is a carrier, probability of having a son that is normal, and another probability of having a son that is hemophilic, so 25, 25, 25 in terms of genotype, but analyzing their children in general. So the probability of having 75% of their children can be normal in this diagram, and only 25% of their children are affected. But I can ask you, what is the probability of having a daughter that is colorblind? In this case, it's 0. Just look at the Punnett diagram. It is 0, okay? The probability is 0. What is the probability of having a daughter that is a carrier? So, daughters, you only have 2 rectangles with daughters there. So you say 50% of having a daughter that is a carrier. Okay? What is the probability of having a daughter that is normal? Normal means that the daughter does not carry any recessive gene. Right? So the probability is also 50%. So I can also ask you, what is the probability of having a son? You're analyzing son only. A son, not children. Children means son or daughter. But in this case, a son, okay, that is colorblind. It is 50%. Okay? This is how you do this. It is 50%. Okay? Because I only have 2 probabilities of having a male here. Either hemophilic or normal. So 50%. You understand? This is how we do this. Okay? Alright. Thank you guys. Enjoy your day.